Hello everyone, here we'll be discussing vector functions and space curves. To be quite honest, this section shouldn't take too much time. The video shouldn't be that long, that is. Hopefully, fingers crossed. And the reason I say that is because it's a very intro of a section. And what we'll be discussing makes a lot of sense, I think. The only iffiness is actually when we get to space curves, which we'll discuss later. But for right now, let's cut to the chase, like usual. So I say here a vector function is a vector r. So usually we write this as r of t, though, whose components all depend on some variable, say t. In other words, r of t is the vector whose components are each functions of t. F of t, g of t, h of t. And this is the common notation we'll be using. So for example, r of t is t cubed, ln of 3 minus t, and radical t. So for example, we can evaluate if we like, just like we evaluate normal functions, or usual functions, I should say. So imagine we want to find, I don't know, r of 1 or something like that. So what is r of 1? R of 1 is the vector 1 cubed, which is 1, ln of 2, well 3 minus 1, which is 2, so it's ln of 2, comma the square root of 1, which is just 1. So just in particular, just to show that we can evaluate functions at a particular value, so we can evaluate a vector function at a particular value for t. Perfect. Now, as far as limits go, we won't really be doing any problems in this section, but it's helpful to know the definition for limits for vector functions, and it's exactly what you may think. Basically, the limit as t goes to a of a vector function is just the limit as t goes to a for each component of that vector function. So namely, limit for f of t, limit for g of t, and limit for h of t, each individually. And then from there, we can actually state the definition for continuity at a particular point. So we can say r of t is continuous at t equals a if this holds. So if the limit of as t approaches a of r of t is equal to the evaluation r of a. Awesome. So that's all I really wanted to say as far as introducing what a vector function is. And now we'll take a look into what space curves are, which is basically just the graph of vector functions. Well, kind of the graph. We'll see right now. And then from there, we'll look at some pretty extravagant examples. Okay, so here I try my best to actually define what a space curve is. Space curve basically is just some curve in three-dimensional space that's defined by a point that's followed by a vector function. But here I kind of describe it a little more formally. So I say a space curve is the set C for curve of all points x, y, z in 3 space, such that x is f of t, y is g of t, and z is h of t, where t is in some interval I, where f, g, and h are all continuous on this interval I. This symbol, if you haven't seen before, just means subset. So this is just saying that I is some interval in the set of all real numbers. That r, of course, means the set of all real numbers. So for example, it could be the open interval 0 to 1. It could be the closed interval 3 to infinity or something like that. But it's some interval in R. But namely, we want H, G, and F, G, and H to be all continuous on that interval. Right, so we want no breaks in our curve, basically. Now, just to give you a visualization of what this kind of looks like in general, so at some point I'll probably stop labeling this x, y, z if we just remember the labeling, the usual labeling that is. The space curve, what we generally typically think of is some curve that just kind of occurs like this. So this would be representative of C. Now, in particular, we're looking at a curve that has a specific direction, kind of like we saw with parametric curves, if you've seen those. That's in chapter 10, by the way. And so I've drawn these arrows to kind of show the direction. But if we pick a particular point on this curve, x, y, z, for instance, I'll just call it P for point. And if we take a look, let me show you in green here, at a position vector from the origin of space, of 3D space, to that point, and call this r, then this is actually r of t. In other words, for different values of t, r will actually trace the point. So imagine this green arrow kind of following the point as we go along. So the direction and magnitude of this vector changes, and the arrowhead point of the vector will actually land straight up on the point as it travels the space curve, basically. So that, I think, is a really nice way of describing that. So now, for this next example, we're going to describe some specific space curves defined by these given vector equations, or vector functions, I should say. So let's take a look. So the first one is asking us, well, they're all asking us to describe the curve. But the first one is giving us this, which should look really familiar to us. These are each linear in t, so this is actually describing a line. And we've definitely seen this before. In fact, really, if you look at the numbers in front of t, this describes the vector that we're parallel to, and we call that v of t. Or, well, actually, we'll just call it v, I'm sorry. And what v is, again, is just the vector whose components are the coefficients of t, which namely in this case are 1, 5, 6, and whose position vector is r. I guess we can call it, we usually call it r naught, I believe. And in this case, it's going to be 1, 2, negative 1. So let me just say that knowing that v is this and r naught is this, then we can describe this by the line with point 1, 2, negative 1 parallel, or in the direction of, to the vector v. 1, 5, 6. So that's how we would describe that. And if you remember from that section, we actually said that we're able to represent any line as a vector equation, r of t equals, well, it would be r naught plus, let me write that off to the side here. So it's r is equal to r naught plus t times v. That's what we had. And in fact, we can actually split this up to be just that. So if we were to split this up, this would be the vector 1, 2, negative 1 plus t times the vector 1, 5, 6. Perfect. And notice, we indeed have that this is r naught, and this is t times v. These are vectors, of course. Nice. So this is just representative of a line. Great. And we described the line. I'm not going to try to draw that out. This next one I will, though. So let's see. So, of course, notice this is in IJK notation, not in the component form. We could write in component form if you want. It doesn't take too much effort to do that, so let me just show that off. This is just the vector whose components are cosine of t, sine of t, and t. Now, if we just set these equal to x, y, and z, so this is our x component, this is our y component, and this is our z component. Let's take a look at x and y. And there's something to notice, actually, about cosine and sine that's actually pretty common to see when you have x being cosine and y being sine, or something of that nature. What we have is actually that cosine squared plus sine squared is equal to 1. So since this Pythagorean identity is true, what this actually tells us that in our case, we have x squared plus y squared is equal to 1. And this is a circle of radius 1. Kind of. Let me kind of explain. So this is a circle of radius 1 on the xy plane. But in three-dimensional space, it's actually a cylinder because it's independent of z. So in reality, this is not a circle of radius 1, but is actually a cylinder of radius 1. So let me try to draw that, I guess over here, we have a little bit of space. I'm not going to label x, y, z. We should know what that is by now, or what they are, I should say. But instead, let's take a look at this circle here on the xy plane of radius 1. And I'm realizing my camera needs to be moved over so you can see the complete image. That looks a little better. And if we're actually to draw the cylinder, we need to lift this up a bit. Let me try to make it a little more straight. And let me get rid of the center part. So this cylinder actually extends indefinitely up and down like this, but this is a cylinder indeed of radius 1, centered at the origin. Just like x squared plus y squared equals 1 is a circle of radius 1 centered at the origin of the xy plane, but in three-dimensional space, we're unlimited in the z direction actually. So that's what the first components tell us. The second component is a little harder to talk about, but essentially what happens is as you plug in values of t, what x and y do is they actually traverse around the circle. So on the xy plane, like we're kind of used to, we have this circle of radius 1, and we start here. Because when you plug in t to be 0, cosine of 0 is 1, sine of 0 is 0, so we get the point 0, 1. And this actually traverses in the counterclockwise fashion. So we have the point kind of doing this. In other words, as t goes from 0 to infinity, and possibly even from negative infinity to infinity, we're basically having the point circle around the cylinder. But as t increases, since t is equal to z, z will increase. So we end up getting this kind of strange shape that you probably have seen before, that actually lifts up and traverses around the cylinder in a counterclockwise fashion. And let me kind of show below. And this shape is actually known as a helix. So this is a kind of spiral shape. I made it look like it bounces outside, but it doesn't actually. It stays within the boundaries of the cylinder. That was just me being a little clumsy. Yeah, it looks a little better. So I'm going to try to draw these arrows just to show that. So hopefully we see that done correct justice. And I hope the explanation was clear on why that's the case. It's because as t increases, since t is equal to z, z is increasing. So not only do we have this happening on the xy plane, but since z is equal to t, then we have this actually, but rotating out in the z dimension. So in 3 dimensions, it should look something like this, and this is known as a helix. Spiral helix, I believe. Okay, perfect. So now we're going to move on to a few more examples, and then that'll be it for the video. Right, so these are going to actually be the last 2 examples we'll see in this video. We want to find the vector function for the following. First, for this line segment that joins these 2 points, and then for this curve that's described here. But for this line segment, this is not just a line, but it's a segment of a line, which is something we could have spoken about in the last video, but it would have made it way longer than it was. That video was an hour plus, by the way. So that's a monster of a discussion. So I didn't actually talk about that. But let me just kind of describe what that looks like. So line segment actually has a very particular equation. Actually, it's a really nice equation. And it has the following vector equation. R of t is equal to 1 minus t times r naught plus t times r1, where r naught and r1 are just position vectors of any 2 points on the line. And here we have these 2 points in the line. In fact, they have to be the endpoints of the line. So here this is going to be, well, let me just say r naught and r1 will each be these in some order, so I'll write that right now. Before I get carried away, let me say that it must be the case that t goes from 0 to 1. And this should kind of make sense intuitively, because as t goes from 0 to 1, this goes from 0 to 1, but 1 minus t will go actually from 1 to 0. Because notice, when you plug in 0, you get 1 minus 0 is 1, and then when you go all the way to 1, 1 minus 1 is 0. So as this goes from 0 to 1, as t goes from 0 to 1, this t will go from 1 to 0. So basically we're going from one point to the other point. It's kind of where this stops. But we need this restriction for sure. So that's important that we have this restriction. This is kind of our interval that we care about. This is what I was saying R earlier, or not R, but I earlier, which is the subset in R. So if you want, you can think of this as I being the closed interval 0 to 1, which is a subset of the real number line. But anyways, that's fine. All right, so now R1 and R0, so let's actually show what they are. R0 is just going to be the vector. Let's pick the first one, 1, 3, negative 2. This is the position vector for that point, which is one of the endpoints of the line segment. R1 will be the position vector for the other endpoint of the line segment, which will have components 2, negative 1, 3. And now all we have to do is actually just combine things and see what we get. So we're going to get r of t is equal to 1 minus t multiplied by the vectors, this scalar multiplied by the vector, 1, 3, negative 2, plus t multiplied by the vector, r1, which is 2, negative 1, 3. So all we have to do is scale in a few things, combine, and that's it. So if we scale 1 minus t into this, that 1 distributed will just be 1 minus t for our first term. 3 distributed is 3 minus 3t. Negative 2 distributed is negative 2 plus 2t. Similarly over here, if we distribute this, or scale in this multiplication of the scalar t to this vector, we get 2t minus t, or negative t, and then 3t. So now finally, we can add these and then we'll get a nice closed form. So we get r of t, I have to squeeze this in a little bit. 1 minus t plus 2t is 1 plus t, because 2t minus t is positive t only. 3 minus 3t minus t is 3 minus 4t actually. And for the last one, negative 2 plus 2t plus 3t is negative 2 plus 5t. Perfect. Now, I'm going to box this, but before I box it, keep in mind we need that restriction as well. So let me say comma, t in between 0 and 1, inclusive. Meaning it can be 0 or 1. So, or equal to, basically. Fantastic. So that was the first part. Now, the second example, which is quite different, asks us to find the vector function for the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y equals, y plus z is equal to 2. Okay, so we can try our best to kind of graph this. In fact, we saw what that cylinder looked like earlier. Cylinder of radius 1 looks something like this. Of course, I'm trying a segment of that cylinder, but in reality it extends indefinitely. Think of like this really long pipe that never ends. But not only that, we have this plane that kind of crashes through here. So if you imagine that, we actually get this intersection. In the intersection, it kind of looks like a circle, but it's not quite a circle actually. Believe it or not, it's actually it's an ellipse. So it's kind of like the stretched out circle, if you will. Now, I'm not going to actually talk about the direction of this. Well, I can actually, because we know x squared plus y squared equals 1 is a circle that's usually traversed in a counterclockwise fashion. So we know it's going to look something like this. But unlike the helix, this is actually closed. It doesn't continue indefinitely. This is just one piece, kind of like how this line segment is just one piece. It's a segment, not an indefinite, continuously going on to infinity curve type thing. Anyways, to actually find the vector function, what are we going to do? Well, we're going to take a hint from the previous example we saw that this really reminds us that x can be cosine of t and y can be sine of t. And this is something I said was a pretty common thing to consider. Of course, cosine squared plus sine squared is always equal to 1. In fact, this is really the parametric equation of a circle. Well, of the unit circle in reality. So we know that from trigonometry, so that should make a lot of sense. Fantastic. So we have our x and y parametric equations. All we need now is our z parametric equation. That's where this steps in, because we can solve for z actually. Notice if we solve for z here, we get what? We get z is equal to 2 minus y. And since we already know what y is equal to, then we must have that z is equal to 2 minus that y equation, which is sine of t. Perfect. Now we're all set. Now we can say r of t must be the vector function whose x component is cosine of t, whose y component is sine of t, and whose z component is 2 minus sine of t. Fantastic. Now, a question you may have is, do we need any restriction? And the answer is no, because if we go from 0 to 2 pi, that's one rotation of this ellipse. But if we go beyond that, we'll just kind of stay within this ellipse. Opposed to here, if we were to go on beyond this interval 0, 1, we'd actually go beyond our line segment into the actual indefinite line that never ends in each direction. Fantastic. So with that being said, that's all I wanted to say as far as this section goes with vector functions and space curves. Really hope you enjoyed this, and I'll see you in the next videos where we'll be discussing more fun stuff. There's a lot to unravel there, so we'll have to take a look and look forward to that. It's going to be a lot of fun. But anyways, like always, hope you enjoyed this. Thanks for watching, and I'll see you then.